My name is Matjaž KUNAVER, and I came from the National Institute of Chemistry, and on the same time also from the PoliMaT, which is a center of excellence in Slovenia. It is also a part of this PLASTiCE as a partner. And the names you can see here on this slide, they are all my friends, my colleagues that work on together with me on those projects or those topics that I will be talking about. As I said, Center of Excellency PoliMaT is a consortium of 22 partners from industry and from the research area in Slovenia. And the main goal is actually, as you can see on the right side, to do some advanced research and to get this critical scientific mass to do something really excellent. And on the other hand, I shall be talking today about the utilization of biomass in a different way than we have heard from the previous speakers, because the idea of our work is to replace a certain amount of, let's say, crude oil raw materials with the materials which are available in Slovenia. And that is the forest material, or let's say the biomass from the forest. Slovenia is the third, the most forested country in Europe. It is covered almost 60%. The area is almost 60% covered with forest. And the main point is that forest is spreading. Half of the annual growth is left in the forest, so it means that we have plenty of raw materials, bio-based raw materials, renewable materials that can be utilized in some, let's say, chemical processes. You are all familiar with the utilization of this lignocellulosic biomass for the production of polymers, ethanol. I would say that mainly they use some enzymatic processes to produce ethanol, and also some pyrolytic processes to produce some energy and so on. But I shall talk a little bit about different applications. These are all pictures, let's say, to illustrate what we can use for our liquefaction process or for use for the change from the biomass to some useful polymeric or monomeric materials. We liquefied waste and broken furniture. We liquefied the leftover after the timber cutting. We could also liquefy this beautiful Amazon.com packaging material, or the corn wastes and so on. Here is one of the known liquefaction mechanisms that are present in this liquefaction process of wood. I would say wood in general, but otherwise we can talk about all these lignocellulosic materials, that is lignin, cork, I don't know, wood chips and so on. Here it is, well, the main point is that you simply depolymerize this cellulosic chain into more monomeric or oligomeric parts, and here you use some glycols to do that, and acid is used as a catalyst. The situation with lignin is more complicated. Again, you depolymerize the very complex lignin polymer into more simple units, and of course, again, we use these glycols in this process. And I would say that here we still don't know exactly what is going on during the liquefaction process. What is the product? As you can see from this slide, it is a dark brown liquid with about 3 kilopascal-seconds viscosity and with a lot of hydroxyl groups available for further reactions. And that is the beauty of the product, because these hydroxyl groups can be used in polyester synthesis, in polyurethane chemistry, and some other applications. You can see here on this slide how it looks like in our lab. It is a simple glass reactor heated up to, let's say, about 180 degrees. It lasts, classic process lasts about 2 hours, but our invention is to use the ultrasound to increase the speed of the reaction. And instead of 2 hours, we finish the liquefaction in 20 minutes. So it means that this input with the ultrasound is very effective for this process. And you can also see what are the main, what is the, let's say, the general formulation that we use for this liquefaction process. Here glycerol is written in red color because glycerol that we use in this process can be obtained from the biodiesel production. So at the end, if we calculate how much renewable resources in a typical formulation we use, we can get almost 97% of these renewable resources for this depolymerization or liquefaction process. We've also, our partner in this research also made or constructed this pilot plant, so we have a capacity about 800 or 1,000 kilograms of liquefied wood per day, and that is already some, it's quite a nice amount to start some really industrial tests and industrial applications. The liquefied product is the particles which are left in this product are mostly crystalline cellulose, because it is so difficult to liquefy it because of this crystal structure and so on, that if we want to get rid of also these small particles, then the reaction would take place a little longer. But if the further utilization of the product is really not so, let's say, so difficult, then we can leave it as it is. Well, these are three different applications that we have done with this liquefied wood. One is adhesives for the furniture industry. The other is the production of polyesters from this liquefied wood, and on the basis of these polyesters we also produce some polyurethane foams. And the third one is to use the liquefied wood directly as a fuel in turbine engines for the production of electricity. Well, as I said, the liquefied wood has a lot of OH groups, so why should we not use this material as a polyol in the polyester, in a polyester synthesis? So we use it, as you can see from this typical formulation, liquefied wood, some adipic acid or phthalic anhydride or something like that, and of course we need some catalysts for the transfer esterification process, and at the end you've got a very nice product with higher viscosity, higher molar mass, and on the other hand lower OH group, OH value, which is also quite desirable in the reaction with isocyanate. On the other hand, we found out that when we use this polyester from the liquefied wood for the polyurethane production, that we need something else to add. So we did also this polyethylene terephthalate depolymerization and prepared another polyester. Again, we had some improvements in this process because the usual product from this depolymerization with, for example, ethylene glycol or something like that, you could easily get some crystallized product. We use this polyethylene glycol 400 for this depolymerization process, and it was a big improvement. First of all, the product was liquid. Second, it was already a long chain, a long polymer chain, which is favorable for the, let's say, dimensional stability in polyurethane foam. Here is a typical formulation for this polyurethane foam production. As you can see, it is a classical, some polyester, some catalysts, silicon surfactant. We used water, not ethanol and not hexane anymore, because water is, after all these, let's say, optimization processes and so on, water was quite suitable. And at the end, here is the product. The thermal conductivity is in the range of the standard polyurethane foams. The compressive strength is also in the range of these commercial products, and the density is quite favorable. We think that such isolation panels could easily be made on the basis of this polyurethane foam. This is, let's say, our goal in the next 6 or 9 months time.